Welcome. This video is going to look at Chapter 4, Section 3, where they talk more about the actual covalent structure and some of the properties associated with that. So the way to represent a covalent bond is something called the Lewis structure, which shows both the bonding pairs and the lone pairs of electrons around the element symbol. And as I said, these are commonly used to represent covalent bonds, and you can either use a line to represent the bonding pair, or you can use two dots, but commonly you use a line to represent the bonding pair and then two dots to represent the lone pair, so then it's easy to pick out bonding pair versus non-bonding pairs. And you represent all valence electrons for each atom in the molecule. And I like to use the same method to determine every Lewis structure, since sometimes you have multiple bonds or sometimes you have these dative or coordinate covalent bonds. So my method is to determine the central atom, and it's going to be the first one listed in the formula unless it happens to be hydrogen, which of course can't be a central atom with just one electron. And then I determine the total number of valence electrons available when I add up the valence electrons for all the atoms in the formula. Then I draw the central atom and I bond each of the other atoms to that central atom with just a single bond. I fill in the necessary number of lone pairs. I count the total number of electrons used and compare it to the total amount that I had available. And if I use more electrons than I had, that lets me know I need to share more, so I can add a double or a triple bond to the central atom as needed. If it happens to be an ion, then I need to pay attention to the charge, because if it's a plus charge, I need to subtract that many electrons from my starting total. And if it's negative, I get to add those electrons to my starting total. So I don't know if it'd be helpful to take a screenshot of this so you remember as you start drawing these again, but that's kind of my quick analog on how you do it, or on how you draw these Lewis structures for covalent substances. So what is a dative bond? It's also called a coordinate covalent bond, and it occurs when one atom donates both the electrons used in the covalent bond. And it really doesn't matter to us, especially if you use the method I just talked about, but it can kind of mess you up. So why would one atom donate both? Because it takes less energy and it makes both atoms more stable. And if you really care about where the dative bond is, you can denote it by using an arrow showing that one atom donated both. Like in carbon monoxide, one of the triple bonds is a dative bond, and I could show that by showing the arrow pointing from oxygen to carbon. But since this bond behaves exactly like any other bond once it forms, it really isn't important. So it isn't very often that we care if there are dative bonds or not. Okay, real quick reminder of octet rule exceptions. Sometimes the octet rule isn't followed, and instead it's incomplete or expanded. And this happens because it still results in a more stable arrangement than if it did not form. And there's actually a good reason, especially for the incomplete octets forming with boron and beryllium. These two atoms are small metals, so normally you would expect them to form an ionic bond with a nonmetal, but they're so small that their electronegativity difference isn't great enough to truly be an ionic bond. So instead, they form a covalent bond with most nonmetals. But the nuclei for boron and beryllium are so close to the shared bonds that a double bond isn't going to be possible. So even though boron has two valence electrons, rather than trying to form a double bond or a dative bond, it's just going to form those single bonds and go with an incomplete octet. And beryllium is going to do the same thing with its three valence electrons. It's just going to form three single bonds rather than trying to crowd the nuclei close enough to form a double bond or any kind of dative bond. So this results in an incomplete octet of 4 and of 6 electrons, and the molecule is said to be electron deficient. And what that means is these molecules are going to be able to accept an electron pair from a molecule with a lone pair, or pairs such as NH3 or H2O. So they will readily bond with other things and complete their octet. Expanded octets, on the other hand, are when you have more than 8 around it, and these can only happen with period 3 elements and bigger, because you need the d orbital to form up to 18 valence electrons, or 9 pairs. The other thing that we need to be reminded in Chapter 4 is this VSEPR model, or the molecular shapes. And VSEPR stands for Valence Shell Electron Pair Repulsion Theory. And it's based on the idea that all pairs of electrons repel each other, so they spread as far apart as possible. And that's true for both a lone pair and bonding pair. But really, electron domain is a better term than electron pair, since a double bond acts like a single pair or a single domain. So an electron domain could really be a lone pair or a bonding single pair, or two bonding pair in a double bond, or three bonding pair in a triple bond. Those all act like just a single electron domain. And the shape is actually determined by the total number of electron domains, not pairs. Lone pair are not confined by two nuclei pulling on them, so lone pair will repel more than a bonding pair can, just because they have more room to push each other apart. They're not confined to that space between the nuclei. So this means the repulsion between pairs does vary. Lone pair and lone pair will repel each other the greatest amount. Lone pair and bonding pair the next, and then bonding to bonding pair will have the least amount of repulsion because of their confinement by the nuclei. Repulsion is what creates the bond angle, which then determines the molecule shape. So here's molecular shapes you should know. A linear is when you have one or two bonding domains, and it's going to create a 180-degree bond angle. And by one or two, I mean if it's just two atoms, there'll just be one domain between them. But if you have three atoms, you can also have a linear shape if there's just two domains between the three atoms, just one bonding site off of each side of the central atom. Trigonal planar is when you have three bonding domains around the central atom, and they're all going to be 120 degrees apart in a single plane. But similar to that will be a bent or a V-shaped is when you have three domains, but one of those is a lone pair and two bonding pair. So that lone pair is going to push the two bonding pairs slightly closer to 117 degrees. And instead of seeing a slightly asymmetrical trigonal planar, we see it as a bent or V-shape because we don't see that third domain. We don't see that lone pair up there. So then tetrahedral is when you have four bonding domains, and they're all, four electron domains, and they're all bonding sites, and they would be an equal distance apart of 109.5 degrees. But if you had those four domains with three bonding pair and one lone pair, those three bonding pair are going to get squeezed slightly closer to 107, and we're going to see that as trigonal pyramidal because we don't see that last lone pair attached to the center atom. And if we had that same arrangement with four bonding domains, but two were bonding pair and two were lone pair, now the two bonding pair would get pushed even a little closer to 105 degrees, and we would call that a bent shape. So you should be able to reason your way through these shapes and recognize them, and be able to reason the angles as well, because 120 degrees gets squeezed slightly closer to 117 if there's a lone pair, and the tetrahedral gets squeezed tight, slightly closer with one lone pair, and a little closer yet with two lone pair. Okay, so polar molecules all depends on the polarity of bonds to start with, and then the shape. So polarity of bonds, remember, depends on charge separation within the bond, which depends on the electronegativity of the two atoms. So if you have a charge separation because of different electronegativities, then you may have a polar molecule. Polar molecule depends on the presence of any polar bonds and then how those polar bonds are distributed or the shape of the molecule. Nonpolar bonds result in nonpolar molecules, always. You can't possibly have a polar molecule with nonpolar bonds. Polar bonds, though, don't always result in a polar molecule. If they have equal polarity, so it's between like atoms, and if these like atoms are arranged symmetrically around the molecule, you will get a non-polar molecule. So this would be the case with a linear molecule, a trigonal planar, or a tetrahedral molecule. Even with polar bonds, if we have equally polar bonds arranged symmetrically around that molecule, the molecule is still nonpolar. But when you have polar bonds with unequal polarities, so they're not all the same atom attached, or if they're arranged asymmetrically like they are with bent or with trigonal pyramidal molecules, then you have a polar molecule. And polar molecules are said to have a net dipole movement. In other words, you're going to have a more positive end to the molecule and a more negative end to the molecule. Resonance structures occur when a double bond can be located in more than one position in a molecule. So it has to be between like atoms, but there's more than one position where those like atoms are bonded together. For example, ozone O3 is 3 oxygen molecules bond together, and it bonds with 1 single and 1 double bond. But who's to say where the double bond is, which side it's on? And in fact, what scientists have found is ozone contains 2 equal length and equal strength oxygen bonds that are considered 1.5 bonds, because they're not a true single or a true double. The second pair of electrons is now thought to be delocalized. Just like electrons are delocalized in metallic bonds, they're thought to be delocalized in these double bonds, these resonance bonds that can occur in more than one place, and they're able to move throughout the molecule, which actually gives the molecule greater stability than if it had one longer and one shorter bond. So to represent this idea, the best we can do is draw all the possible structures called resonance structures, but keep in mind the real structure is actually a resonance hybrid. It's a combination of these two structures. That second pair of electrons, or that double bond, isn't rotating between the two places, but instead that extra pair of electrons is spreading out across the molecule, delocalizing. Another structure to bring up with covalent bonds is this idea of giant molecular solids. They're also called network covalent structures or macromolecular structures, meaning giant molecules. Most molecules have a defined structure and exist individually or independently from each other, like O2 molecules floating around us, H2O molecules. But atoms like carbon and silicon have 4 bonding electrons, and it would take about the same amount of energy to either transfer them as an ionic bond or to share them. So carbon and silicon, being more to the nonmetal side, tend to form a crystalline lattice that looks like an ionic structure but doesn't truly transfer the electrons, so it's acting like a covalent bond in there. But because it's a crystalline lattice, it can go on indefinitely. Still a covalent bond, the size is limitless, but the properties are more like an ionic compound. So the melting point and boiling point are going to be higher, closer to what we'd expect for an ionic, since the covalent bond has to actually be broken instead of just stretched on these big molecular solids. They could be good conductors, or they could also be good insulators. You can bring out either characteristic, and they tend to be very hard, like diamonds. And in fact, carbon has several of these giant molecular solids it can form, because it can form what are called allotropes, different versions of the same element in the same state. Well, silicon tends to form silicon dioxide or quartz, which, as you probably know, is a pretty hard solid and is a common giant covalent structure around us. So here's some allotropes of carbon. You should be able to recognize these different allotropes. And you should check out page 144 for the rest of this chart, where it talks about the actual properties and uses of each allotrope. As I said, an allotrope is a different form of the same element in the same state, like oxygen gas and ozone. So carbon has several: graphite, diamond, fullerene, and graphene. Now, graphite and diamond you're probably familiar with. Graphite being a real two-dimensional structure. It's kind of in layers. We use it in lead because they slide over each other, so it writes really well. And then diamond, I think you're familiar with. It's a 3D structure. But then this fullerene is where each carbon atom is bonded in like this soccer ball configuration of hexagons and pentagons, total of 60 carbon atoms. And then graphene is kind of like the two-dimensional version of fullerene, where each carbon atom is covalently bonded to 3 others, but just in one plane or in 2 dimensions. And as I said, check out page 144 for all the uses that people are coming up with these. And in fact, it leads into this whole new field of nanotechnology, nano meaning really small. So nanotechnology is a field that deals with atomic scale manipulation of matter. In other words, it's building and changing things atom by atom, which is what really exciting stuff is going on with this graphene and then graphone. In fact, if you've heard talk about them making your new tablet and your new phones with screens that don't break, that's graphene that they're thinking will be able to do that. So it's some really cool stuff happening in this field.